In this video, we're going to look at populations and samples. We'll look at the difference between a population and a sample. We'll look at gathering together some random samples. We'll look at measurements of property distribution in populations. So things like how many of the population have red hair, how many of the population wear orange coats. And we'll look at the distribution of those, what proportions or probabilities occur in populations and in samples taken from those populations, and the relationship between those measures in the sample to the measures in the population. And I'll also introduce you to the idea of sample proportions in the term of p hat. So this little symbol here, you pronounce p hat, and our population proportion p. But first, let's look at the difference between a population and a sample. In statistics, there's a clear difference between a population and a sample. What we've got here is a picture of some people. So if we took these people to be a little group from the whole people in the world, then our population that we were looking at would be all the people in the world, and this group would be our sample. In statistics, however, you can take any size group that you like to be your population. So, for example, we could say that the people in this picture are our population, and I want to take a sample from that population. So the large group that we're measuring from, the group that we want to know something about, that is our population. The group that we want to know something about, that's our population. And then a group from that population that we're going to collect some data from, that's our sample. So say, for example, we wanted to know how many people in this picture are wearing orange jackets. We could take a sample of people and see how many in that sample are wearing orange jackets. We could take a different sample over here. We could take another sample over here to work out how many people there are wearing an orange jacket. Now, given that you could probably count the people in this picture that are wearing orange jackets, it seems like a little bit of a pointless activity. But this statistical approach, using a sample of a population to get some information about the population, is used widely in the world where populations are large and sometimes unknown. Anyway, let's talk about the different sizes that we have for populations and samples and how we write those in statistics. So normally what you have is your size, the number of things in your sample is normally less than the number of things in your population. And I'm saying normally because I'll tell you just something in a tick. Let's just squeeze this down. Okay, so the symbol that we use for the number of things in a sample is lowercase n, and the symbol that we use to represent the number of things in a population is capital N. Now, I said before that a sample is a group from the particular population. You can in fact have a situation where your n, lowercase n, is equal to your uppercase n. The size of the sample is in fact the size of the population, and you get that when you have a census. So when we do a census in Australia, instead of having to take some samples to figure out how many orange coated people we have, we can just ask a question in the census and then we will know for sure how many there are in the population. Let's talk a little bit more about using a sample to work out characteristics of this population. Statistical inference is the name that we give to the process of determining the properties of a population by analysing data collected from samples of that particular population. So we've got a population over here of little yellow and green people, and I've labelled that section population. Now we can't see the whole population, it heads off in that direction there, but we've got a little bit that we can see here. So if we wanted to work out some information about the population, we don't know what size it is, but we know that we have a symbol for it, capital M. And we don't know what proportion of that population is little green people, but I'm going to label that as a P for the proportion of green people that are in that population. So if we wanted to work out exactly what proportion of green people we have in our population, what we do is we take a random sample. And in this case, I'm going to take a random sample size of 4. So I'm just going to randomly pick 4 of them. 1, 2, 3, 4. And then I'm going to work out, for the sample that I have, what is the proportion of green people in that sample. And the symbol we use for that is P hat. So in this sample of 4 here, 1 out of my 4 is a green person. So my sample proportion for this sample is 1/4. And therefore, I can say that based on this sample, it's quite probable that 1/4 of this population, including the bits that I can't see, are green people. To make a better estimate of the population proportion, I'll choose another sample. I'll throw these guys back in and randomly choose, whoops, not all of those, randomly choose another 4. So you can't see, but I'm closing my eyes and I'm picking some. 1, 2, 3, 4. And so for this one, the sample proportion is also 1/4. And you can keep going and collecting sample proportions to give you a better and better idea of what the actual proportion is for the population. And that's what we refer to as statistical inference. And we would say here that our P is going to be around about 1/4. Statistical inference. So to summarise what we've got so far, we have a population, and I've squeezed the whole population into this particular circle. So this is our population. And our population has a particular number of members, and the population has a particular proportion of whatever characteristic it is that we're interested in. And from this population, we take a sample. And this sample also has a particular number of members in it, and it has a proportion all its own called the sample proportion of how many people in this sample population have the characteristic that we're looking at. So we have 2 sets of information. One, measurements from our population, and the other are measurements from our sample. And in statistics, because these measurements come from different groups, if you like, our population measurements we use capital letters for, and we refer to them as parameters. For our sample information, we use lowercase letters for our sample, and we refer to these measurements as statistics. So in the past, all of the information that you hear about statistics, sometimes the word has actually been used when they mean parameters for a population. So statistics is the most commonly used word to describe measurements of a set of data. But when you're working in a mathematics field, statistics means measurements of the sample. So S for statistics and S for sample. And measurements of a population, P for population, are called parameters. And the process of statistical inference goes like this. We start with a population, and from that population we take a sample. We measure things, information, measure things about this particular group of people, and we find some statistics, and then we use those statistics to make inferences about the population. And another word for inferences is almost predictions. From our sample proportion before, we had a quarter of our population was green people, and from there we said, well, okay, if a quarter of our sample and our couple of samples was green, then maybe this population should have a proportion around about a quarter of green people. Our actual population proportion, capital P, is 4 green people, 1, 2, 3, 4, out of a total of 17 members of the population. So this is our N value. And our sample statistic with a proportion of a quarter is quite a good estimate of our population parameter. So I guess the obvious question is, why not just measure the population? Why go to this hassle of selecting a sample, finding some measurements, and then trying to guess what the answer is for the population? Well, the reason for that is simple. Not everything in life is easy to predict. Have a look at these thumbtacks. Of all the thumbtacks in the world, what proportion of them are sitting with their point in the air? If you like, what's the probability that if I had a handful of tacks that I dumped them on a table, there's my little tack, I dumped them on the table, what proportion of those tacks would be sitting with their spike in the air? There's no way to measure that, really. Well, there is, but not within the scope of this course. So the easiest way to do it is to do a few samples and measure their proportions. So if we did that for these pictures, these are the proportions that we would get. So the first one is close to a third, so 0.3. The second one is close to a third, so let's say 0.3. The problem comes with this sample, where this is closer to a half, 0.5, than it is to 0.3. So what is the probability that that tack is going to land with its little point in the air? Somewhere between 0.3 and 0.5. So even though we can't measure all the tacks in the world and figure out how many there are sitting around the world, what proportion of them are sitting up, we can make an estimate from here. A bit of a rough one, but still an estimate. And what about this for a question? What's your thumb look like? Which one of these is your thumb? And how would you go about figuring out what proportion of the people in your suburb, city, state, in the country have what's referred to as a hitchhiker's thumb? So when we're taking a sample from a population, we need to make sure that if we're after a random sample, and a random sample is one where every member of the population has the same chance of being selected, then we need to make sure that the processes that we're using are giving us random samples where everybody has the same chance. The other type of sample that sometimes get mentioned is whether something is a fair sample or not. If something is a fair sample, it's one that is representative of the population. And then we start to get into sticky areas of what it actually means to be representative of the population. So if I wanted to know what the favourite ice cream flavour of choice was for a particular school, how do I select my sample? Do I just randomly generate some numbers and pick people at random? Do I go through and select the same number from Year 7, Year 8 and Year 9, Year 10, same number from each? Do I just choose the people that are coming in from the northern gate? Or do I just select people whose names start with the letter P? How do I pick them, and what are the problems with all of those selection methods? All of them have issues. Not everyone gives every member the same chance, and then some of them aren't representative of the particular population. And that's what some of the questions are about in 17A, thinking about the sampling method that is used. How do I select these people? Is it fair or not? And is it random or not? Let's have a look at generating some random selections. Actually selecting a random sample is something that is extremely difficult. We have what we call true random events as well as pseudo random events or pseudo random numbers. So you can get some true randomness if you use some physical phenomenon. And it's true, we don't know how actual the randomness is, but it's kind of considered true. So you can use things like atmospheric noise, you can use thermal heat generated from a particular place in the earth. If you're interested in finding out more about physical phenomena, or actually to use atmospheric noise to generate some random numbers, you can use random.org. If you're interested in learning more and going down the rabbit hole of randomness, go to their website, click on Learn More and Introduction to Randomness. But this true random number generator that is sitting here on their website actually uses the atmospheric noise, so noise in the atmosphere, and the level of noise in the atmosphere to generate random numbers. So if you put your lowest number that you want to have to your highest number that you want to have, and then press generate, it will select a random number for you. So say we have 16 students in the class and we need to randomly select 3 students. I would put minimum of 1, maximum of 16 for our 16 students and press generate. It would give me a result, and then I would use that number to select whichever student corresponded to that. And then I'd generate another one, and another one, and another one. And if it generated the same number, I would just ignore it and then continue on. So that's using some physical phenomenon to generate randomness. The other thing that you can do is you can use a computational algorithm. So your computer will generate random numbers for you. Excel does it. Your phone, depending on what you're running, will do it. But your CAS calculator definitely generates some random numbers for you. But because it's an algorithm, there's a pattern to what's going on. So it's not a true random, it's actually a pseudo-random. And so if you wanted to have a look at how it works, if you go to your CAS calculator and look under the probability section, you'll find random as one of the options. If you just select that, it will spit you out a random number in a variety of different formats. But what you need to be aware of is that it actually uses a formula to generate a new number from the number that's currently on your screen. So you actually need to set a starting value. because when they come out of the factory, every CAS calculator is starting with the same number for its random number algorithm. So if you haven't seeded, we call it seeding, if you haven't seeded your calculator with a new number and you pressed random, random, random with the person beside you, you would generate exactly the same numbers. So that is no way random. So if you wanted to generate random numbers with your CAS calculator or with a computer program, you need to seed that program so that it makes you give different numbers to somebody else. So it starts further along in the sequence. So let's have a look at what happens on your CAS calculator when you use the random commands. So you can see that with the first one, I have seeded my calculator with 2222. So you just need to put a 4-digit number in here. The second option on your CAS menu is number, random number. And if you use this, it will just generate a random number between 0 and 1. And you can just press enter, enter, enter onto your calculator and it'll just give you a list down there. The next one is random integers. And in this one, you put the smallest number you want as your random number to be generated as, the largest value, or the maximum value. So you want values here between and including 2 and 10, and you want 3 of them. And then it'll generate it as a list over here. The next one is your binomial, random binomial, and this will generate you a set of numbers with a mean of 10 and a mean of 10 from a sample of 10 with a probability of success of 2, and I've asked here for 4 outcomes, and so it's generated them here. So if you wanted to do some sampling from a population that has a binomial distribution on it, you can use this command to generate sets of numbers for you. And finally, the other one that I'm going to talk about extremely briefly is doing the same idea, randomizing from a normal distribution with a mean, I've picked 30, and a standard deviation, I've picked 7, and then I've asked for 5 results. And so it's randomly selected 5 results from a normal distribution that has a mean of 30 and a standard deviation of 7. And we'll talk about this a lot more in another video. There are a couple of questions in the exercise that ask you to use a random number generator. You can use random.org and the noise of the atmosphere, or you can use your CAS calculator. It's completely up to you.